Hi. What I'm going to do in this video is review logarithms, exponential form to logarithmic form to exponential form, graphing logarithmic functions, exponential functions, no, just graphing logarithmic functions, and then solving some equations either in a logarithmic form or exponential form. So I'm working off the end of topic 6 review. Those of you who have that, the first thing you're going to be asked to do is evaluate an expression. Before you can evaluate an expression, you need to be able to comfortably move back and forth between exponential and logarithmic form. So if I have something in logarithmic exponential form, like 7 to the third power equals, pens. $343. I can switch that to logarithmic form using the same, it looks like log. The base over here is the 7, so base 7, that's a subscript of 343 equal to 3. So if I'm asked to go the other direction, log base 5, 1/25 equals -3, -2, sorry, -2. Dropping my pens has got me a little flustered. Okay, so then we move back to exponential form. The base here, the 5. The exponent is the -2, and that is equal to 1/25. So these two things are equivalent. Anything to the negative exponent, you reciprocate it. So since this is a -2, we reciprocate it, becomes 1/5 squared, and then 5 squared is 25. So the negative means we reciprocate. That's why it becomes a 1/25. So if I'm asked to evaluate logarithm, on your review worksheet, it would be questions 1 through 6. So if I'm asked to evaluate, say, the log base 4 of the cube root of 4, I'm trying to figure out what goes here, right? I'm trying to figure out what it's equal. So I'm going to switch it to exponential form. So the 4 is our base. The exponent is what I'm looking for. This number is what I'm looking for. And then 4 to the cube root of 4 goes here. So then how can I write the cube root of 4 as 4 to some power? Well, the cube root of 4 is the same as 4 to the 1/3 power. So the answer is 1/3. Log base 4 of the cube root of 4 is equal to 1/3. Log base 8 of 1/64. What does that equal? So the bases are 8. The exponent, that's the number that goes here. That's what we're looking for. And then that's equal to 1/64. Okay, so 1/64. 64 is the same as 8 squared. And then as I talked about up here with the negative exponent, I would rewrite this as 8 to the -2. So the answer, the log base 8 of 1/64 is equal -2. Okay, so if you're working through your review packet, it would be questions 1 through 6, like those. If you're simply asked in any of the questions to switch to rewrite as a logarithm or rewrite as an exponent, that's what this stuff is here. So in your review packet, that looks like number 12 and number 19. Oh, we'll look at 19 in a minute. Number 12 and number 13. Okay. So I'm going to erase this stuff, but I'm going to leave up the exponential logarithmic form for use later. Okay, so if I'm asked to graph the log base 2 of x, I need to make a table of values. So it doesn't really, to make a table of values in log form is difficult, especially if we have a log base 2 and not a log base 10 or natural log, something we could use a calculator to evaluate. So what I'm going to do is I'm going to switch this from logarithmic form to exponential form. So the base is 2, the exponent is y, and that's equal to x. And then I'm going to make my table of values from this equation. So these two equations are equivalent. They're the same. They say the same thing. So since y is the exponent, those are the numbers I'm going to pick over here. So -2, -1, 0, 1, 2 are my y values. 2 to the -2 power is 1/4. 2 to the -1 power is 1/2. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. And now I have some ordered pairs to make my graph. So logarithms and exponents are inverses of each other. That's how come we can switch back and forth between exponential and logarithmic form. So right here, I'm just switching from logarithmic form to exponential form so that I can easily make a table of values. They should be inverses. So 2 to the x power looks like this. The logarithm base 2 has the point 1/4, -2. Let's go with this. 1, 2, 3. 1, 2. Okay, so 1/4, -2, 1/2, -1, 1, 0, 2, 1, and then all the way over here, 4, 2. So this is the function I'm drawing, the log base 2 of x, but you can see that they're inverses of each other. This is y equals 2 to the x. This is y equals log base 2 of x. They both have asymptotes. The exponential function has an asymptote here, and it comes up from the asymptote. The logarithm has an asymptote here. So as I graph logarithms, I want to make sure to keep in mind there's an asymptote here. And you'll see that if you try to calculate values where x is smaller than 0 or equal to 0, there's no way to plug in x equals 0 right here or anything negative. Okay. So what if I'm asked to, I'll just write it over here. What if I'm asked to graph log y equals log base 2 of x minus 3 plus 1? Well, the -3 shifts the graph to the right 3, and the 1 shifts the graph up 1. So this graph right here that I just graphed, I'll draw it in blue, needs to get shifted to the right 3 and up 1. So I just take each of my points here to the right 3 and up 1, to the right 3 and up 1, to the right 3 and up 1. And now my asymptote is at 3. So I have this asymptote here at 3, and my graph looks like that. Ish. So without a grid on my board, it's kind of difficult. But this is shifted to the right and up. And now the asymptote, excuse me. And now the asymptote is at x equals 3. So you'll notice that 3 is what makes this equal to 0. That's where your asymptote occurs, when your function has an input of 0. Okay, so let's talk about the blue one that I have graphed here. What is its domain? Its domain would be everything greater than 3, not equal 3, greater than 3. Its range would be all real numbers. It has an x-intercept. at 1, 2, 3.5 and has a y-intercept. It does not have a y-intercept. Sorry. And then its asymptote is at x equals 3. And its end behavior, as x goes to infinity, the function is going to infinity. So as x goes to infinity, y is also going to infinity. When we go to the left side of the graph, x can only go to 3. It can go past 3. The function's not going to pass that vertical asymptote we have drawn in there. So as x goes to 3, y goes to negative infinity. So this is all for this function here that's been shifted to the right, 3 and f1. If you are asked to calculate with a calculator a value like the log of a number or the natural log of a number, you're literally just finding that button on the calculator. So if I'm asked to calculate the log of 628 with a calculator, you would just literally punch those buttons on your scientific calculator. If you don't have a scientific calculator, Desmos has a great one. And so then you would literally just type the log of 628 in the calculator to give you the answer. The same with the natural log. If I'm asked to calculate the natural log of 0.55, just find the natural log button on your calculator. If you're using Desmos scientific calculator, just type in ln. You just the letters ln. So this one is 2.798 if we round to the 10 thousandths, and this is negative 0.5978 if we round to the 10 thousandths. So we're also going to be solving some equations. Some of them are simple, like just switch it from logarithmic to exponential form and solve, or switch it from exponential form to logarithmic and solve. So if you're on your purple worksheet, this is number 13. If I have the natural log of x is equal to 5.4. I'm going to take this equation from logarithmic form and switch it to exponential form. What's the natural log's base? It's the log base e. Of x equal to 5.4. So e is the natural number. E is 2.71828182818. Goes on forever. Like pi, it is irrational. So we're going to switch from logarithmic form to exponential form. The base is our e to the 5.4 power equals x. So this is an exact value answer. This is the answer. This is exactly the value. You could estimate, or I'm sorry, not estimate, you could give me a decimal approximation. If you type this into your calculator, e to the 5.4 power, you should get 221.406, rounding to the thousandth power. So as we solve equations, I'm going to solve some more equations here. Your job is to decide, am I in logarithmic form like we are here? Then I should switch to exponential form to solve. Or am I in exponential form, which is what I'm going to give you in the next problem. And then I would switch to logarithmic form to solve. So again, if you're working on your worksheet, number 14 says 10 to the x plus 3 power minus 4 equal to 8. So this is in exponential form. You can see the 10 to the x right there. That's our exponential base and exponent. So what we need to do is isolate this 10 to the x plus 3 by getting rid of the plus 4 or the minus 4. We add 4 to both sides. And now we are in basic exponential form. The 10 is our base. The x plus 3 is our exponent. The in this case, it's in the y position, and then the 12 is over here. So if I rewrite this in logarithmic form, it's log base 10 of 12 equals x plus 3. From here, this is just a calculator problem because base 10 is your logarithm, that button in your calculator. So this is just the log of 12 with a calculator, and then we'd subtract the 3 from both sides. So I would type in the log of 12. The calculator is going to automatically put in your parentheses around the 12. And then the minus 3 is outside of those. So it's outside of the log of 12 function. So you would subtract the 3 from it like that. And then if you estimate this value, again, this is an exact value. What I'm about to give you is the decimal approximation. So negative 1.921 would be the decimal approximation. So as you're asked to solve equations, your job is to decide, are you in logarithmic form, in which case you switch to exponential form and solve, or are you in exponential form and you switch to logarithmic form and solve? Sometimes when you are in exponential form, you don't want to switch to logarithmic form. For example, if I have, this is number 22 on the purple worksheet, yeah, 16 to the 2x plus 1 equals 8 to the x minus 1. So what's the difference between that equation and this equation? This equation is clearly in exponential form, 10 to the x plus 3. That's our exponential base and exponent. This is clearly in exponential form. 16 is our base to the exponent, but this is also in exponential form. So in this case, I don't want to switch to logarithmic form. It's not going to make things easier for me if I switch to exponential form, or to logarithmic form, sorry. So what I'm going to do instead is I'm going to create a like base. You might recognize that 8 and 16 are powers of 2. 16 is 2 to the 4th power, and 8 is 2. So I'm going to replace the 16 with 2 to the 4th, and I'm going to replace the 8 with 2 to the 3rd. Now I have a base 2 here and a base 2 here. Recall that the exponent to an exponent rule, shortcut rule, I should say, is that you can multiply 2 times 4 to make 8, because x squared to the 4th power means x squared times x squared times x squared times x squared, 2, 4, 6, 8 makes 8 of them all together. So this is just a shortcut rule. The multiplying, 2 times 4 is 8. I'll leave that there for just a second. So we're going to distribute this 4, multiply it by the 2x plus 1, distribute the 3, multiplying it by the x minus 1. And then on the left side, I have 2 to the 8x plus 4. And on the right side, I have 2 to the 3x minus 1. So erasing this. So what's the rule if I have like bases? If I have 2 to some power equals 2 to some power, then the exponents, 8x plus 4, must be equal to 3x minus 1. And then I would just solve. I have to subtract the 3x from both sides. Subtract the 4 from both sides. And I get x equal to negative 1. Your job then is to just double check that if you plugged it back in, the two things would in fact be equivalent, and they would. So that's how you solve questions on that back sheet number 22. I'll continue with that back side. Just one other thing you might need when you are solving an equation, if you switch something to logarithmic form, like we did in that last a couple examples back, and it isn't a log base 10 or log base e, the natural log. What happens if it's a log base 4? How do you calculate that approximate value if you don't have a log base 10 or a log base 4? You do what's called change the base. This is equivalent to the log of 12 divided by the log of 4. Now, when I say the log of 12, I'm talking the log base 10 of 12. So your basic log button on your calculator. So this is the log base 10 of 12 divided by the log base 10 of 4. You just need to be super careful when you type that into a calculator that you are closing parentheses. So the calculator might automatically put a parenthesis around the 12 in front of the 12. You close that before you hit the divide, and just be careful. So you should get 1.7925 if we round to the 10,000s. So if I have, that was number 19. This is number 20. If I have 7 to the x equaling 489, 486, sorry. This is number 20. If I have this, and I want to switch it to logarithmic form, it would be log base 7 of 486 equal to x. Now, this is just the basic logarithm exact answer. If I need to switch it in, use the change of base formula to find its decimal approximation, I would type it in log of 486 divided by the log of 7. So the log of the argument, the bigger number, divided by the log of the base, the smaller number. And you should get approximately 3.1791. This should be approximate symbol. So its exact value would be this, log base 7 of 486. The exact value would be this, the log of 486 divided by the log of 7. And its decimal approximation is that right there. So depending on what you're being asked for. Also, you could use the natural log here. When you change the base to log base 12 over log base 4 or log base 496 over log base 7 or log of 7, you could use the natural log of 12, the natural log of 4, the natural log of 486. It doesn't matter as long as you use the same thing for the top and the bottom. So the same thing we did here, where we changed to like bases and then dropped the bases so that the exponents were equal, we can do the same thing with a logarithmic equation, as long as the bases are the same. So if, for example, on your purple worksheet, you are looking at number 23, the log of 15 minus 2x equal to 2. Oh, hang on. Let's pause on this one. Let's go talk about the rules, the properties of logarithms first, and we'll come back to that. Okay, so the properties of logarithms, there are 3 properties. The first one is the product property. That says if I have the natural log of 8x, so that's the log of 2 things multiplied together, I can rewrite that as, as the natural log of 8 plus the natural log of x. Then I have the quotient, which says if I have a log base 10 of 3 divided by x, I could rewrite that as the log base 3, the log base 10 of 3 minus the log base 10 of x. So notice the base is the same here. So natural log is log base e, log base e, log base e, log base 10, log base 10, log base 10. So if I have the third property is called the power rule. So if I have my log base 2 of y to the 5th, the power rule says I can multiply that 5 by the log base 2 of y. So think of it as flying down, coming down in front. So that power that was here on the y is now multiplied in front of the logarithm over there. And again, the same idea, same base, log base 2, log base 2. Okay, so if I am going to expand an expression using these, oops, using these rules, if I have the log base 7 of r to the third t to the fourth over v squared, I might use my quotient rule first, or property first, and change this to subtraction. What it would look like then was the log base 7 of r cubed t to the fourth minus log base 7 of v squared. Then this becomes a product rule, right? Property, log base 7 of r to the third plus log base 7 of t to the fourth minus log base 7 of v squared. Again, I'm carrying my base all the way through. So that multiplication using the product property turned into addition. This quotient division turned into subtraction using the quotient property. And then the last property would be our power. So the 3 comes down in front. So this is 3 log base 7 of r plus 4 log base 7 of t minus 2 log base 7 of v. Now, this is not one of the problems on your purple worksheet, but it is similar to the questions set on 17A. Then we can go the other direction. I'm going to leave those there. I'm going to erase this in just a second. We're going to go the other direction. We're going to take something that's in expanded form, so like this, and work our way back to its compressed form as a single, rewrite it as a single logarithm. So if I have 5 natural log of 7 plus 1/2 natural log of, let's change this to a variable. Let's say this is a x and this is a y. Okay. Oh, hang on. Like that. Okay, so it doesn't matter which way we work from whatever direction. The 5 becomes the exponent on the x, the 1/2 becomes the exponent on the y, the 3 becomes the exponent on the z. So it looks like natural log of x to the 5th plus natural log of y to the 1/2 minus natural log of z to the 3rd. And then to put it into one, these two are multiplied together. So that's the natural log of x to the 5th times y to the 1/2. And then this subtraction means division. So the natural log of x to the 5th, y to the 1/2 over z to the 3rd. The only other thing I would do is this 1/2 power is the same as the square root. So anytime you have a rational exponent like that, it would change to a radical. So a 1/2 power is a square root, a 1/3 power is a cube root, and so on. If this was a 5, this would be a 1/5. Okay. Okay, so back to erasing the properties. Back to solving that equation I started to do a minute ago, which we need that power property to solve. The logarithm. So on your purple worksheet, this is number 23. So this is the one I wrote up a minute ago. The reason I paused is because we need the power rule or property to make this an x squared. Now, once you have this, so we talked about it a little bit ago with the exponential equations. If I have like bases on an exponent, we talked about 2 to this exponent, 2 to that. So as long as the bases are the same, the exponents have to be equal. The same is true if I have the log of this equal to the log of that, and the bases are the same. As long as these two bases are the same, these two arguments have to be equal. They have to be. So what I'm going to do is just drop the logarithms, and I have this equation. And then I'm going to put it all on one side. I like to write it as x squared. It would become a 2x minus 15 equal to 0. I like to add the 2x over, subtract the 15 over, so that the x squared stays positive. We're going to factor this. We're going to rewrite this in factored form. So we're looking for the factors of negative 15 that add to make 2. So 1 and 15. You can't divide by 2. 3 and 5 works if the 3 is negative and the 5 is positive. So x squared minus 3x plus 5x minus 15. And then this, what I did was I rewrote the 2x as a 3 and a 5, right? I haven't changed the value. Those two combine to make a 2x. So then to factor by grouping, I would group together the x squared and the 3x, group together the 5x and the 15, and then factor out their common factor. So here, if I factor out an x, I'm left with x minus 3. Here, if I factor out a 5, I'm left with x minus 3. And then if I factor out the x minus 3, I'm left with x plus 5. So those are your two factors. Let me erase the stuff over here so we can finish this. And so my solution would be using our zero product property rule, x minus 3 equals 0 at 3, x plus 5 equals 0 at negative 5. Now, you can have what's called an extraneous solution. With logarithms, we have to be careful. We cannot take the log of 0 and we cannot take the log of a negative value. It's undefined. So anything that causes 0 or a negative number when it's plugged back into the original equation would be considered extraneous. If I plug negative 5 in right here, I have 2 times the log of negative 5. That's undefined. Is not, you can't calculate it. So this is considered extraneous. And then you could just double check that when you plug in 3 right here, you get positive there. Do you also get positive over here? And you do. Okay. That's everything. So I think that's everything we have to cover.